In this lecture, we will be covering area computations in polar coordinates. So let's consider a region bounded by three curves. First, we have radial lines, theta equals alpha. So here we will have this line, theta equals alpha. And remember, these type of radial lines are formed because we have this angle alpha, and all polar coordinates along this line through the origin have at least one representation with this angle theta. And then for the other radial line, we have theta equals beta. And we would have this as the angle beta. Then we have the polar curve r equals f of theta. And that we can think of something like this. And we're interested in the area of the region bounded by these three curves. And we will call that area A. So, let's think about how we would set this up. So first, let's consider a subinterval, theta I sub 1, theta I, inside that interval alpha beta. So we would have these radial lines like this. So here we would say theta equals the constant theta I, and here we have theta equals theta I minus 1. And remember, we had this radial curve, or this polar curve, r equals f of theta. And we're going to think about restricting our area to just the piece in between these two radial lines, theta equals theta I minus 1 and theta equals theta I. So we're interested in this area here. Now, to get this area, we would have to deal with this boundary on the top right here, coming from the curve r equals f of theta. But that's a bit tricky to deal with. So why don't we think about, instead, using a circular slice. So suppose that we were to choose, say, a point here. And then we used that to make a circular boundary. So when we say circular, think circle centered at the origin. And now we can think about getting the slice. Think of it like a slice of pizza. The key thing is now you have a circular boundary, and that's coming from the circle centered at the origin, with the radius determined by this point on that boundary of the polar curve. And what we're concerned with is the area. The area of this slice. Or we should say area of this slice from a circle of radius, we'll call it Ri star. So this radius here, this distance, we will call R sub I star. The way we choose R sub I star is by choosing a representative theta I star inside the interval theta I minus 1, theta I. And then we set R sub I star to be F evaluated at that theta sub I star. So our theta sub I star, the way we've depicted it here, would be this angle depicted in brown. And so we plug that theta I star into the curve R equals F of theta to get that radius for this circular slice. Again, think of it like a slice of pizza. Now we want to calculate the area. So the area, A sub I, of this slice. Now, we know that the area of the circle is pi r squared. And how much of the circle do we have when we just have this one slice? Well, we know to spin once around, we have 2 pi radians. And we know the radial range here is going from theta I minus 1 to theta I. So this ratio gives us the fraction of the circle. And so we can write it this way. Fraction of the circle. And again, the area we know is pi times the radius, Ri star squared. And the fraction of the circle we just argued was theta I minus theta I minus 1, also called delta theta, over 2 pi. And so this becomes, noticing that the pi's cancel, we get 1/2 Ri star squared times the change in theta. And this gives us the area of this ith slice. Now, we want to think about this in a larger scope. Now that we have the area, or I should say, this slice approximates this shaded area that we want here. But we now have a formula for the area of that circular slice. Let's think about doing this in mass. So we have our same graph, but now let's partition the interval for the angles, alpha beta, to theta 0 can be alpha, smaller than theta 1, theta 2, up to theta n, which is beta. And we can have a regular partition. So delta theta is the width of this interval alpha beta divided by n. And so the idea now is we're going to do this approach of doing this slice over the entire region. So we're going to have n of these slices. So our partition geometrically will look something like this. And we still have our theta equals alpha and theta equals beta radial lines. And now we are going to approximate on each of these subintervals. In the way we just did, we're going to approximate the areas that we seek using these slices from circles. So we will have this slice from a circle to approximate the area we seek on each of these subintervals. And the way we want to think of this is put your integral calculus hat on and think about if we can get an expression that adds up the areas of all these slices from circles, that sum will approximate the area we seek, and then we will let n go to infinity, and in the limit we'll get the exact area, and our sum will turn into an integral. So that's where we're going, but here, this is just a description of this picture using the setup we did before. So we have our partition for the range for the angles. We choose a representative angle in each subinterval, just like we did on the previous slide, and use that representative angle to get the radius for our slice of a circle. And then we construct all of these, and we have our area overall, the area we seek, can be approximated by the sum, I going from 1 to n, of these AIs. And again, each AI is a slice, or we'll say this is the area of a slice. And we know that we've seen from our previous slide, we know that the area of this slice is 1/2 Ri star squared times delta theta. And so this gives us the shaded region area depicted here. So now that we have this approximation for the overall area, we then note that the Ri stars, the radii, came from evaluating the function f at the theta I stars. So we make that change. And then we note that this is a Riemann sum. And so we can let n go to infinity, which forces delta theta to go to 0. And recall we did a regular partition. So our delta theta was beta minus alpha over n. So letting n go to infinity means all of these widths shrink to 0. And this Riemann sum becomes an integral. And we get the integral here, which gives us the exact area of the polar region we're working with. And so we have the integral from alpha to beta of 1/2 times the square of f of theta d theta. Let's see how you would use this in an example. So consider this Limacon. So this is given by r equals 3 plus 2 cosine of theta. So we're not constructing the graph of it, we're giving it here. You would use the techniques we learned in polar graphing lectures to actually graph this. But we want to find its area. And the way to set this up, remembering that we have that formula, area is the integral from alpha to beta of 1/2 f of theta squared d theta. We have three things that we have to find. 1, the f of theta. 2, the lower bound of integration. And 3, the upper bound of integration. And a way to think of this, when you work on this, looking at the geometry, is take a ray emanating from the pole, from the origin, outward through the region. And think of this like the dial on a clock. And what we want to do is think about, where does this dial leave the region? And we see it leaves the region here on the function. It leaves the region on r equals 3 plus 2 cosine of theta. So we know that's our function. F of theta is 3 plus 2 cosine of theta. But then we want to think about, what is the angular range over which you have to turn this dial to sweep out the region? And we can think of that here as, bring this dial down. A natural way to do it would be to say, start it at an initial angle of 0. So we can start it here. And then we spin that around. Again, think of it like turning the hand on a clock. And we have to go from 0 radians to 2 pi radians. So that gives us single spin to sweep out the area of this region. And that's what we want. We want this area enclosed by the graph of this Limacon. And so with this information, we can then apply this formula to get that the area is equal to the integral from 0 to 2 pi of 1/2 times the quantity 3 plus 2 cosine of theta squared d theta. And we can work out that integral to get this area. In the next lecture, we will look at an expanded version of this. But the key thing to recognize in this is the idea of using this slice from a circle to approximate areas.